All right, this is the 5.3 natural exponential function pre-class video. We're going to be looking at solving exponential equations again, but this time using a base e, which we're going to define in just a minute, and applications with continuous compounding. So terminologies and symbols dealing with natural exponential functions, we're going to look at what's called the compound interest formula. This is the one that is covered in the in-class notes part of section 5.2. And it is that a equals p parentheses 1 plus r over n to the nt power. Now, this is your future value. This is your present value in terms of investing money or borrowing money possibly. R is your rate as a decimal, like if you have a 6% interest rate, then you would have 0.06. N is the number of compoundings that happen in a single year. So if they compound you quarterly, we would be putting in a 4 for that. And then N and T get multiplied together. T is the number of years that your principal is invested. So if you do it quarterly for 10 years, that's 40 separate compoundings that occurred during the life of this investment. So what happens if the rate and the total time invested are fixed, but the interest period is varied? So what if we fix the rate and time, but we change the number of compoundings? So suppose $1,000 is invested at a compound interest rate of 9%. Find the new amount of principal after 1 year. So we're keeping it very simple in a single year. If the interest is compounded quarterly, which is 4 times a year, monthly, which is 12 times a year, weekly, which would be 52, daily, which would be 365, hourly, which is going to be 8,760, and if you compounded your interest every minute of the year, it would be 525,600 times. Now, because we've left t as a year, notice that the exponent is matching the denominator here. That does not always happen. That's just because we're doing this for a single year and not multiple years. So you can see that they've plugged this in, and these are the differences in the complete future value. So your future value, when you only look at the compoundings, you notice that after a while, compounding more and more does not significantly change the value of the future. So notice these kind of get stagnant at 1094.17 when we were at the hours and minutes, and it was only 1 cent different when we did daily. So what we want to look at is that after we reach an interest period of 1 hour, the number of interest periods per year has no effect on that final amount. If the interest had been compounded every second, the result would still be this because the decimal places are changing beyond the first two, which are how we are rounding. So the amount approached a fixed value as in increased interest is said to be, now this is the key word for us, compounded continuously. So that's the big word. I'm going to highlight that if I can get my pen to work. This thing's not one to agree with me today. So compounded continuously if the number n of time periods per year increases without bound. In other words, you never stop the compoundings. They would continually, it's like going almost like, think about infinity. Every time you compounded one more time, find another second in between there and compound again. So this is kind of looking at if we only focus on, so let's say our interest rate is 100%, so 1. And we have a dollar investment, and all we're looking at is that n, the number of compoundings changing, and then it's still 1 year, so because they said t equals 1. So what they did is they let n increase without bounds. So notice we're just using multiples of 10 here. And what was discovered is that this is approaching a specific number. Now, this is kind of also like pi. So this is a special number where this is a non-repeating, non-terminating decimal. And it is found by taking the limit of this. So we don't know calculus yet, but in calculus they show that as n increases without bound, the value of this expression approaches a certain irrational number that we denote by e. So this is our financial number, essentially, because it has to do with this compound interest formula, whereas pi has to do with circumference and diameter of a circle. So the number e has been arisen by this investigation, but we approximate it as 2.71828. Now we're going to be using the E button on your calculator a lot when we graph these, so you'll see in class I will reference that when we do our in-class notes. So this is showing the definition of the number E. And all we want to do in this specific pre-video is a couple things. I want to show you the solving equations that we did in the 5.2 pre-video are still the same if you have base E. And then I want to do some continuously compounding interest problems. So if you look at this guy right here, notice this is that property we had in section 5.2. If you have the same base on each side and they are equal to each other and it's a single base, so one on the left, one on the right, then that can only be true if the x and y are equal to each other as well. So when we do this, notice base e is on each side and there's only one of them. So we're just setting 3x equals 2x minus 1. Subtract the 2x over and we get x equals -1. So same thing we were doing in section 5.2, it's just recognizing base e is not a variable, it's a number. E is a number, not a variable. Okay, so we had the regular compounding formula. I'm going to scroll back up and show you that. That's also going to be covered pretty heavily in the 5.2 in-class notes. This is the regular compounding where we know the number of compoundings that are happening in a single year, so we have a very specific value for that, like quarterly or monthly. If you ever see the phrase compounding continuously or continuously growing or continuous compounding, then you're going to be using what we call the PERT formula. So future value, A, equals your principal, P, and then remember, E is not a variable, it's a number on your calculator, it's a button, it's a number to the RT, where R is also still going to be expressed as a decimal, and T is in years. So I've got two examples to go through with you. It says if $100 is deposited in a savings account that pays an interest rate of 6.5% per year, compounded continuously, find the balance after 10 years. So just because of what I underlined, I know I'm using that A equals P times E to the RT formula. So we need to determine if $100 is our A or our P. So since it's being deposited, that is our P. We know our rate is 6.5, which you can write as 6.5%, but we need to turn that into a decimal. So move the decimal 2 places to the left, 0.065. The time is 10 years. We are looking for A. So A equals 100 e to the 0.065 times 10. I will usually work out the exponent portion because usually that can be worked out nicely. But typically we will type all of these things in without doing any rounding. We don't want to round any of our steps along the way. We want to type it all in. So this is 0.65. Now, depending on your calculator, you may have an E to the X button or an E to the blank button. So depending on which one you have, you need to make sure, and it might be something you have to use the shift key for. You want to practice this to know that you have it right. You want to type in E to the 0 and make sure it gives you 1, because remember, any base to the 0 power, any non-zero base, I should say, to the 0 power is 1. So if you want to check on your calculator, you'll want to do E to the 0, or some calculators you have to type in 0 first and then shift to E. So you want to make sure whichever way you're doing it, it's giving you back the answer of 1. That's kind of calibrating your calculator and making sure you're using it correctly. So on mine, I'm using the computer calculator. I have to put in the 0.65 first because it is kind of backwards. And then I would, and I know you guys can't see all of this, but I'm going to raise it to the E power, or E to this power, I should say. It's hard to talk and do this at the same time. Second, there we go. And then I want to times this by 100. Now, a lot of calculators, you can just type this directly in, 100 e to the 0.65, and you'll be fine. So this is 191.554. I'm going to write 3 decimal places, and I'm showing that I'm rounding it, because we're going to round this to 2 decimal places usually. So the 4 would not bump the 5 up, so this is going to be $191.55. That's our future value. Now you think, wow, that's not that great, because, you know, I let it sit for 10 years and I didn't even double my money completely. But if that was $1 million you deposited, it would grow at this same rate. So you'd almost have $2 million. So it is a perspective of, we didn't put much money in, and you pretty much just said, here's $100. I'll see you in 10 years, make it grow. So without you doing anything, the money almost doubled. All right, so then the last one for this is how much money invested at an interest rate of 5.5% compounded continuously will amount to $15,000. So So a couple things different here. Amounting to means we want the future value to be 15,000. That means we don't know, it looks like our present value or our principal. Our rate is 0.005 since it's 5.5%, and our time is 4. And it again is the PERT formula because they are using compounding continuously. So 15,000 equals P e to the 0.005 times 4. So we're trying to solve for P. Now I usually go ahead and work out that exponent, so 0.005, oh sorry, that's supposed to be 0.055. What happened? I don't know what happened when I wrote that. I think I said 5.5 and I didn't write 5.5. All right, and then that changes this guy. It's just miscopying while I'm talking. All right, so we need to do 0.055 times 4. 0.055, I'll clear that out. Times 4 is 0.22. So this is 15,000 equals P e to the 0.22. I am dividing by that e to the 0.22 because e is a number. So we're trying to get P by itself. So we're going to divide that over. Now, you again will want to enter this all into your calculator at one time. And you guys will probably have access to calculators that are better than the one on the computer because I do need to do it in a little bit of a funny way to get it to work out for me. So I figured, and I don't ever clear out my calculator while working because that will round you too early. So once I typed this in, so you would probably type in 15,000 divided by e to the 0.22 using your e button. I'm going to write this out to 3 decimal places. So it's 12,037 and then 0.781. Now, this is an issue when you're rounding and solving for P. We do not want to follow the typical rule that says the 1 will keep this an 8 because that is a thousandth of a penny or a thousandth of our cents that we're going to be losing if we do that, because this is not exactly 0.78. If you are solving for P, whenever you're solving for present value, you want to round up no matter what because it is better to overreach your goal than to be under your goal. If you're shorting yourself even the slightest amount each and every year or each and every compounding, you're not going to make it to 15,000. So when solving for P, we always round up regardless of typical rounding rules. And this is so we don't short ourselves of the goal. So that's the why. Okay, so this would be 12,037.79 if you want to be in cents, or if they told you, well, let's just put in a whole dollar amount, we would make sure we bumped this up to 38, again, regardless of this being a 0.7 after it. So when you're solving for P, you want to make sure you overreach for that goal instead of underreach. And that is it. That is all that I have for this pre-video. I hope you enjoyed.